If that interpretation proves correct, Earth's oceans may not represent an isolated evolutionary experiment. They may instead belong to a broader family of planetary oceans scattered across the solar system, hidden beneath ice, circulating slowly through rock, and sustained by the same physical processes that shape our own deep sea. Section 2. Water, rocks, and the movement of life between worlds. Once multiple ocean worlds enter the picture, a deeper question naturally follows. If water and chemically active oceans are common throughout the solar system, how isolated are those environments from one another? For much of the 20th century, planets and moons were treated as largely closed systems. Each world was assumed to evolve mostly on its own, with only minimal exchange of material between planetary bodies. Modern planetary science has steadily eroded that assumption. Evidence now suggests that the solar system is far more dynamic, with rocks, water, and organic chemistry moving between worlds far more frequently than once believed. Meteorite studies provide some of the clearest evidence of this exchange. A number of meteorites found on Earth have been conclusively traced back to Mars based on their chemical composition and trapped gas signatures matching the Martian atmosphere. These rocks were originally blasted off the Martian surface by large impacts and eventually crossed interplanetary space before falling to Earth. If solid rock can make that journey, an important possibility follows. Microscopic organisms sheltered inside those rocks might survive as well. This idea forms the basis of the panspermia hypothesis, which proposes that life, or the chemical precursors of life, can be transported between planets via meteorites, comets, and impact ejecta. The concept does not claim that life necessarily began elsewhere. Rather, it suggests that, once life exists, somewhere within a planetary system, natural processes may distribute it more widely than previously assumed. Laboratory studies have shown that certain microorganisms are capable of surviving extreme conditions resembling aspects of space travel. Some bacterial spores can endure intense radiation, vacuum exposure, and long periods of dormancy. Even more famously, microscopic animals known as tardigrades have demonstrated remarkable resilience, surviving the vacuum of space for short periods under experimental conditions. These experiments do not prove that life routinely travels between planets. However, they demonstrate that the physical barriers involved are not necessarily insurmountable. Water itself appears to participate in this planetary exchange. Many meteorites contain hydrated minerals, indicating that they formed in environments where liquid water was present. Comets, long suspected to contain significant quantities of water ice, have been observed delivering both water and complex organic molecules during impacts. Early in Earth's history, when the solar system experienced frequent collisions between planetary bodies, these exchanges may have been far more common than they are today. Large impacts could eject enormous quantities of rock into space, some of which would eventually intersect the orbits of neighboring planets. Over millions of years, a continuous background exchange of material may have occurred across the inner solar system. This possibility changes the context of planetary oceans. If worlds containing liquid water periodically exchange material through impacts and meteorites, then ocean environments may not be entirely isolated evolutionary laboratories. Instead, they may occasionally receive chemical and potentially biological inputs from elsewhere in the solar system. Earth itself bears geological evidence of such bombardment during its early history, the period known as the Late Heavy Bombardment, which occurred roughly 4 billion years ago, involved frequent large impacts across the inner solar system. During that era, Earth, Mars, and the Moon were repeatedly struck by asteroids and cometary bodies. These collisions likely delivered both water and complex organic molecules to Earth's surface. Some researchers have suggested that a significant portion of Earth's water may have been delivered by water-rich asteroids early in planetary history. If so, the oceans that now dominate Earth's surface may partially originate from material that formed far beyond Earth itself. In that sense, the oceans that regulate Earth's climate and sustain its ecosystems may carry a chemical memory of the broader solar system. The deep sea may not only reflect Earth's geology, and atmosphere. It may also preserve traces of a much older planetary exchange, one in which water, minerals, and organic chemistry traveled between worlds long before complex life emerged on Earth. Did you enjoy this essay? Let me know below. Like and follow for more.